Okay, so in this video, we're going to continue finding the Maclaurin series or the Taylor series for some of these regular old functions like e to the x, sine x, and cos x. In the previous video, we figured out what the Maclaurin series was for e to the x. So in this video, we're going to figure out what the Maclaurin series or Taylor series centered at 0 is for sine of x. So remember, our goal here is to write sine of x as that Maclaurin series or Taylor series centered at a equals 0, where each coefficient, we take the nth derivative, evaluate at 0 for that Maclaurin series, divide by n factorial, and then multiply by x to the n. And the way we did this previously was setting up a big table and then figuring out what the nth derivative is, evaluating the nth derivative at 0, and so on. And we're going to do that same exact method here. So let's reconstruct that table. So we'll have n, the nth derivative at x, the nth derivative at 0, and finally that whole coefficient itself, the nth derivative at 0, all over n factorial. Okay, so let's start figuring out what some of these coefficients are. If we start off at n equals 1, and let's go out to, n equals 5. Again, this will work, this process of taking the derivatives, setting up this table, and we'll figure out the Maclaurin series or Taylor series for any function that's differentiable. Here, we're working with sine. So our function that we're considering is f of x is equal to sine of x. So if we take the 0th derivative of sine of x, that's just the function itself. If we evaluate sine of x at 0, well, remembering our trig, this is just equal to 0. So this coefficient is just 0 over 0 factorial, which is 0 over 1, which is 0. All right, let's go to the first derivative. And the first derivative, or the derivative of sine, is positive cosine. If we take positive cosine, evaluate at 0, because it's a Maclaurin series, well, this is equal to 1. So the first non-zero coefficient, we take that 1 and divide by 1 factorial, and that's what that coefficient is. So if we're looking at what sine is equal to, it looks like sine is equal to 0 plus 1 over 1 factorial times x. Let's go to the next term. Well, the derivative now of cosine, or the second derivative of sine, is negative sine of x. Evaluating negative sine of x at 0 gives us 0, so this coefficient is 0. Okay, let's take a derivative on negative sine of x. That gives us negative cosine of x. And well, negative cosine of x evaluated at 0 gives us a minus 1. So what this coefficient looks like is a minus 1 all over the n factorial, where n in this case is 3. So the next term, well, we have really a 0 times x squared. And then we have a minus 1 over 3 factorial times x cubed. All right, let's keep going. Taking a derivative of negative cosine, well, that'll give us back a sine of x. Sine of x, evaluate at 0, just as before. That's equal to 0. So this coefficient is equal to 0. So the next term in our series would be plus 0, x to the 4th. And then taking a derivative of sine again will give us a cosine of x. Evaluating cosine at 0 gives us a 1. And that next coefficient will be a 1 over the n factorial, where in this case, n is equal to 5. So the next term in the series is plus 1 over 5 factorial times x to the 5th. And hopefully at this point you're starting to say, well, we're just taking derivative of sine, we're going to get cosine, we're going to keep cycling back between sine, cosine, native cosine, and going on like that forever. We're also picking up these other bits and patterns in our sine series where we're seeing a bunch of zeros pop in. And well, if those terms are just zero, we don't actually have to include them in our series at all. So let's see what our sine series looks like without those zeros written in. We have that sine of x is looking like right now an x minus x cubed over 3 factorial plus an x to the 5th over 5 factorial. And well, we haven't shown this or gone through those terms. If you want, this is a nice exercise, but the next couple terms in the series, we can actually try to predict from what we see here. And well, it looks like for each of these terms, we're only taking part of x's raised to odd powers. All of the even powers of x seem to be dropping out because those signs evaluate at 0 are all 0. So if we're able to figure out the next term of the series just from that table method, it actually would be minus x to the 7 all over 7 factorial. The term after that would be plus x to the 9th all over 9 factorial. And again, you could go through the table to show this. So at this point, sine, it only has odd powers of x, as well as it only has odd powers of n factorials in each of the denominators of these terms. So we could actually compactly rewrite sine, just like we did the exponential. And we'll talk about this in a minute, but if we're able to write sine compactly, we could do something similar. Now, we're just going to re-index our series to only have odd terms. Because all the even terms or even powers of x we saw drop out. So, some things we can note are, well, we're seeing all these sign changes as well. We have the second term is negative, the fourth term is negative of our series, and then the other terms are all positive. So we're going to have some change in sign. And well, if that first term is positive, we can just write that as a -1 to the nth power. So the first term is positive, the second term is negative, third term is positive, and so on. Again, we're starting our series at n equals 0, not n equals 1. And well, to capture only the odd terms, we would then want x's raised to an odd power. And we can guarantee this is an odd power if we write it as 2n plus 1. Because when n equals 0, well, we're just getting x to the first, which is the coefficient on that term. When n is equal to 1, we'll get 2n, or 2 plus 1, which is 3. So we're able to capture the correct power of x on the second term. And all the subsequent terms will be captured as well. And likewise, since we have the corresponding odd factorial in the denominator, we can write this as a 2n plus 1 factorial in the denominator. And this is our Maclaurin series for sine of x. And well, we can do the same exact process for cosine. Except cosine, you might imagine, or you may guess, well, if sine has all the odd terms, cosine actually captures all of the even terms. So we're not going to go through it here, but it's a very nice exercise. You would do the same exact thing for cosine of x. set up a table, see which terms are there in the resulting series when we take all those derivatives and evaluate them at 0. And if you do that for cosine, what you realize is cosine of x, the series it corresponds to is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial, and so on. And basically what you'll see is all of the cosines terms are all x's to even powers. And we're able to rewrite this in a much more compact series notation, just like we did for sine. The only thing we need to do is, again, re-index our series so that we only capture all of the even terms for cosine. And we still see the same sign changing for cosine, where the second term, the fourth term, the sixth term will all have negative signs, whereas the first term, the third term, the fifth term, all the odd terms of cosine have positives and have positive signs. So we can still rewrite this as a -1 to the nth power, because n we're indexing from n equals 0. And to capture only the even terms, we can write this as x to the 2n power. And we can rewrite that n denominator as a 2n factorial as well. And this is our Maclaurin series for cosine. Again, we didn't go through all the nitty-gritty details for cosine like we did for sine or e to the x, but you can do the same exact table process and figure out what all the non-zero terms will be for cosine. And all those non-zero terms will basically be all the even terms that we saw drop out of sine.